The last talk in this session is about the paper entitled A Cipher Agnostic Neural Training Pipeline with Automated Finding of Good Input Differences. The authors are Emanuele Berini, David Gero, Anna Hambitov, and Matteo Rossi. The speaker is Anna.
Yeah.
Please give your talk.
Thank you. Sorry for the very long title. So in our work, we have dealt with neural distinguishers, and I don't know how closely you followed the work in the past years, but it's in the moment a lot of work to find a new, to apply a neural distinguisher to a new cipher. Last year at AI Crypt, Goa, Leander, and Patrick Neumann have asked the question, can we use differential neural distinguishers as a tool for cryptanalysis, such as SAT or MILP solvers? So in a nutshell, like the motivation for our talk is, can we add a new tool that we call AutoND to have automated generation of neural distinguishers for new ciphers? So the main part of my talk will focus on the obstacles and solutions that we faced in answering this question. Let me give a quick introduction to neural distinguishers. So in general, a cryptanalytic distinguishing attack allows us to distinguish encrypted data from random data. And for this, our distinguisher can detect some feature in the input data that allows it to differ between these distributions. In the context of differential cryptanalysis, it has to distinguish between ciphertexts that originate from a fixed plaintext difference or random. Then a differential neural distinguisher, or in this talk simply a neural distinguisher, is a deep neural network that performs this cryptanalytic distinguishing task. The seminal work on this has been done by Aaron Goa and presented at Crypto 19. And it's considered a seminal work because it challenged conventional wisdom and showed that actually machine learning can produce very powerful distinguishers. They can reach better accuracy than pure differential distinguishers. And he improved also the complexity, time complexity of the 11-round key recovery attack. He compared his neural distinguisher to a full DDT-based distinguisher for which he generated around 150 gigabytes of data in 300 core days of computation. To look at related work, it's nice to look at the basic pipeline because people have worked at every single point of this pipeline. So the first is that we have to generate plain text pairs with either the fixed input difference delta or a random input difference. They are encrypted with a round-reduced version of our cipher under investigation. For example, 5 rounds of spec. This is passed to the neural distinguisher, and the neural distinguisher has a lot of neurons arranged in layers. And in the last layer, we find an output neuron with a sigmoid activation function you can see here, which will give us out the decision if our plain text pair is related by this particular input difference, yes or no. So this work has been cited over 160 times in the last 5 years, and people have applied it to other primitives. People have tried out other neural network architectures. They have worked on explainability, which is a general open problem in AI. They have tried to increase the accuracy of the neural distinguisher, for example, by using multiple plain text pairs per sample. They have also tried to use multiple input difference instead of just one. They have applied feature engineering that's conventionally used in machine learning to make your raw data set more amenable to the neural network. So one feature type, engineering type we can naturally think of is to pass the XOR of the ciphertext. And that will, in many cases, speed up the training, but at the cost of now we lost information. So it's a trade-off. People have also used advanced methods of feature engineering, for example, partial decryption. As mentioned, a rather newer trend is to look at automatization. So could we use this as a tool to assist the cryptanalyst? There's also several automatization libraries like Tagada, Cascada, or our own CLASP. So our goal, as mentioned, was to create this AutoND. So we want to give the tool a new cipher, and then it should perform this whole pipeline for us and give us results which are comparable to the state of the art. The first obstacle we face is right here, that we have to choose some good input difference delta. And if you look at previous work, the main work around explainability was presented at Eurocrypt 2021, because the question what makes delta a good input difference is very closely tied to explainability. You need to somehow understand what the neural distinguisher is learning to pass it an input difference that makes sense for the neural distinguisher. So it's not, in general, the input difference with the best differential characteristic. To understand which pairs are really the good ones for the neural distinguisher, Benamira et al. Have realized easy samples G. And the easy samples are decided with a very high confidence level to belong to the fixed plain text difference. And they have analyzed them in great detail and have related the best pairs for the neural distinguisher in round 5 to truncated differentials in round 3 and round 4. So now how does this help us? So we said, okay, let's generalize this and assume it applies to other ciphers as well. But that means now we have to find truncated differentials. So we approximate truncated differentials by high bias scores. So to find a group of good input differences, we investigate bias scores, and instead of enumerating the XOR of the cipher text pairs over all plain text and keys, we do this over a limited number of samples T. And then we combine this bias score with an evolutionary optimizer. And like this, we obtain a range of candidate input differences, which we then want to pass to our neural distinguisher. The problem is that the optimizer returns a large number of good input differences, and identifying the best one is still not super easy. So we decided to analyze the 10% of the best ones, the 10% of the best ones. And exactly, and they differ a lot depending on the cipher under investigation. For spec 128, there's only one, but for all the Simon ciphers, there's actually many, which are good and need to be investigated. So the next obstacle is the neural training pipeline itself. So if we look at Gore's neural distinguisher, there's a lot of choices that you could call conventional or that you would think translate well to another cipher. So it's a residual network with a fully connected prediction head. It has ReLU activations and a final layer sigmoid. It's trained using MSE loss. But there are also some choices which are more expert or heuristic choices. For example, there is an input reshaping of the 64-bit input into a 4 times 16-bit arrangement. And this is particular to the cipher. There's also a number of hyperparameters. For example, he uses a cyclic learning rate schedule and you need to choose a number of filters, and also an elaborate 8-round training scheme. So he retrains the best 7-round distinguisher to recognize 5 rounds back with another input difference. Okay, we have found more generic solutions that we applied. So we moved to dilated convolutions, which don't investigate neighboring bits, but they investigate bits which are far apart. So in a normal convolution, you look at only neighboring bits, but that is maybe not doesn't make much sense in the context of cipher text. So we use dilated convolutions which look at far apart bits and mix them with dilated convolutions which look again at neighboring bits. The cyclic learning rate schedule, we found out we can substitute with something that is also conventionally used in machine learning called Amsgrad. And then we resolved to use only a very simple training pipeline where we take the best distinguisher of round 5, for example, apply it, retrain it on the round 6 data and so on until we no longer detect any signal above random. We took over, took over Gore's simple polishing step. So he retrains with 3 different learning rates with a higher number of samples, and that should generalize well to all ciphers. Okay, we have implemented this in our tool, which we call AutoND, and you can access it either via our repository, or you can also use Clasp to run the AutoND pipeline. Then let me present the results that we got and conclude. So for spec 32, we can retrieve the optimal input difference that is also used in Gore's paper. For the first time, we have achieved to reach 8 rounds with over 51% accuracy. That was before not possible, except for with really advanced approaches. And we can improve the accuracy to match Gore's accuracy with only using our simple polishing step. For spec 64, we reach 8 rounds like previous work, but they have used 128 ciphertext pairs. For spec 128, we have obtained the first 10-round distinguisher. In our work with Simon 32, we achieve similar results as Bao et al., but with a simpler training pipeline. And as mentioned, there's this AI crypt work, and it has reached 2 rounds less in the automatic setting, but when they use extensive manual optimizations, they surpass our work. For Simon 64, we can reach 1 more round than previous work, even though they used more ciphertext pairs. But if you use 8 ciphertext pairs and exploit really cipher-dedicated information, you can still get ahead and reach 1 more round. For Simon 128, we achieved a 20-round distinguisher. For Gimli, we achieved an 11-round distinguisher, surpassing 8 rounds achieved in previous work. And we note that this is due to the input difference. The design document of Gimli also mentions a 12-round differential characteristic. For height, we obtained the first published neural distinguisher covering 10 rounds, and the paper that presents height also mentions a 10-round property, but with a much higher number of needed ciphertext pairs. We ran AutoND in the related key setting, and in this setting, we obtain a 14-round distinguisher. For Catan, we reached 69 rounds, which favorably compares to previous work. And also, if you use more ciphertext pairs, we can surpass it. We also note that we can obtain a 71-round distinguisher, which is still 7 standard deviations above randomness. So that should also be considered valid, I think. For present, we obtain a 9-round distinguisher, which surpasses previous work, even though it used more ciphertext pairs. And also, there is a best differential characteristic mentioned in previous work for 9 rounds. For TIA and XTIA, we find distinguishers for 5 cycles equivalent to 10 rounds, and they do share the same input difference. For TIA, we improve over previous work. For LIA, we obtain the first neural distinguisher reaching 11 rounds, and there is also a differential characteristic mentioned in other work for 11 rounds. So let me conclude the talk. I have presented to you AutoND, and we can find competitive distinguishers to highly specialized approaches, in particular spec 32 and Simon 32. we could provide new distinguishers for several primitives. And also we could improve over the state of the art for present, Catan, TIA, and Gimli. You can find our implementations as mentioned in 2 ways. And with that, I thank you for your attention.
Thank you for a nice talk. So are there any questions?
Thank you for your talk. A quick question about the related key differential attack you mentioned. How did you decide on the related key difference?
Yeah, it's part of the optimizer actually. So instead of only finding a good input difference, like a good input difference for the plain text, you also search for a good difference for the key. So it's part of that.
So you trained with plain text and keys. So you gave the optimizer both the random keys that you picked and random plain texts.
Yeah.
And the second question, how does this work relates to the work of Dino et al. From Eurocrypt 2023 that found automatic tools for finding differentials as a black box?
Oh, I'm afraid I don't know that work.
Thank you.
Sorry.
Thank you for your talk. So my question is, sorry, what are the steps that one should take to use Auto-ND for like other ciphers?
Yeah, that's you just need to provide an encrypt function. So you have to download Auto-ND and then you have your Python implementation and you have to provide the encrypt function of your cipher.
Thank you.
Are there any questions or comments? I have a question. Do you think neural differential based key recovery attacks can be improved by providing your neural distinguishers?
Yeah, I think it's a really good question. So that was where we first wanted to go to, like, look at the whole chain up to key recovery. But I think it is very clear this is much more complicated. So there, David, who is co-author, he has combined the optimizer with MILP and retrieved, for example, the difference that Gore has used in his key recovery attack to prepend rounds. But yeah, I think to generalize, this is much more difficult.
Oh, okay,
Yeah.
thank you. Are there any questions? Okay. So let's thank all the speakers again.